Guys, in this video we shall see another problem on LeetCode. Check completeness of a binary tree. So given the root of a binary tree, determine if it is a complete binary tree or not. In a complete binary tree, every level except possibly the last is completely filled, and all nodes in the last level are as far as left as possible. You can have between 1 and 2 power h nodes inclusive at the last level h. So let's first understand what's a binary tree and a complete binary tree. So binary tree means a tree having two nodes, right? So if this is a root node, it should have two children. So that's a binary tree. Now what I mean by complete binary tree? That means if you have a tree like this, all the levels, there is a first level, second level, third level, and fourth level. One, two, three, four. So all the levels except the last one, all these levels except the last one must be full, complete. That means each and every node must have two children. It should be a complete tree. And coming to the last node, coming to the last level, it should be complete from the left side, as far as from the left side. So if you observe, if you start from the left side, if it has left children, then right children, then all are null. That is fine. So if in case there is a node like this, then if you observe from left to right, left children, right children, empty, this is null. Again, both nodes are null here. Here you are encountering left node as null, but there is a right node. So this is not a complete tree. It should be complete from the left side. So once you encounter a null node, all the nodes further to that in the right side must also be null. Only then you can tell a given tree is a complete binary tree. So in the given question, how do we find the whether a given tree is a complete tree or not? So for the given question, yeah, I just pasted the diagram over here. So if you observe, all the nodes except the last node, that is this node and this node. This all the levels, sorry, all the levels except the last level till here. All the levels, yeah, all you can see it's a complete tree because both the children are present till the end. But when you see the last level, yeah, you have to check from the left side. It should be complete from the left side, right? So in the last level, as far left as possible, all the nodes in the last level must be present. So left node is present, right node is present, left node is present, then last one right node is not present. Yeah, that is fine because it is complete from the left side. And once you encounter a null node, there is no other node without a null node. So it is a complete binary tree. And coming to the second problem, so yeah, so all the levels except the last level, you could see. Um, Yes, two children are present and it's a complete binary tree. And coming to the last, and the subtree you can tell. And coming to the last level, you can observe from left to right when you traverse. Left node, right node. Then here it is null. After you encounter null, you must encounter only null nodes right to that, right? But if you observe here, the right node is not null. It's not null. So that means this is not a complete binary tree. Not a complete binary tree. So how do we solve this problem logically? What's the logic to solve this problem? So for this you will be using BFS. So BFS means if you take this example only, let's consider this example. In the BFS first level, you consider so you'll get 1. And in the second level, you'll get 2 and 3. And in the third level, you will get 4, 5. After that, 6. And coming to the right node, it's null. So this is nothing but null. So this is 1. This is BFS for this tree. And the other tree, Here, if you observe the first level, yeah, 1. Then come to the second level, 2 and 3. Fine. Coming to the last level, 4, 5, and here it is null node. 4, 5, 4, 5, null, and then 7. So here, if you observe while doing wafers, first we will traverse 1, yeah, fine. Then 2 and then 3, fine. Then 4, 5, 6. After that, you will traverse null. So after this null, are you encountering any non-null node? No. So, yeah, this is a binary, complete binary tree. But here in this case, for this tree, you traverse like 1, then 2, 3, then 4, 5, and here you are encountering null. So once you encounter null, all the nodes further to this whatever you traverse should be null. But you can see it's a 7 is a non-null. It's not a null node. Not a null node. Hence this is not a complete binary tree. And one other example, yeah, I would like to give is like other scenario 1, 2, 3, 4, 4, 5, then 6. There are no nothing 7. Okay, 8, 9, 10, 11. So if you observe in this example, till here it's the all the nodes except the last nodes, last level. Sorry, all the levels except the last level. So this is the last level. Here all the levels. Here if you observe, this is 1, fine, 2, 3, 4, 5, 6. After that, here you observe you are getting it as null. So this is not a complete binary tree. So all the if this is the nth level, all the n minus 1 levels should have two children compulsory. Two child nodes are must. But for the last level, it should be complete only from the left side. That means if you encounter a null somewhere in between, then all the nodes next to that in the right part of the last level should be null. That's one case. So now for this, as I said, we'll be using BFS and we need a queue first, which will follow first in first out order like FIFO. So once you have queue, as I write the code, we'll explain and later we'll trace that same code with an example. So let's move to the implementation part. First, as I said, we'll create a queue of type Trino. Let's name it as queue and new linked list. So we'll be using linked list implementation of the queue interface in Java. So linked list. Once you have this, now you have to add the root node to the queue. And one more, we need um, a boolean value named as flag that is set to false. So why do we need this? This is required because if flag is set to false, that means a node is not a null node. Once you encounter a null node, you set the flag equal to true. So that is where we require the boolean value flag. Now we shall start with the while loop. While the queue is not empty, what do we perform is we'll create one more node, tree node called node equal to queue dot pull to remove the element from the queue. Or it's a first in first out. So very first element which will be inserting to the queue, that element will be removed now. It's a header element. And next, after that, you have to check if node equal to null. If node equal to null, then you set flag equal to true. So once this is done, otherwise else part will be if flag equal to true, then return false. So what does this do is, at first you add a root or one into the queue, right? So once you do that, you check whether queue is empty or not. No, it's not empty because one is present in the queue. Then you check whether tree node equal to queue dot poll. Then you perform this operation. So node will be equal to one now. You remove the element from the queue, header element from the queue, and that will be initialized to the node value. So once you have node equal to one, that means node is not null now. You go to the else part. So if in case if you get some removed element equal to null, here you may get removed element equal to null, right? Here in this case. So if you get node equal to null and you set the flag equal to true, then you go to the next loop again. And after this here, and q dot add of root dot left and q dot add of root dot right. Okay, so here you encounter node what node equal to null and you set the flag equal to true now. So next we will encounter 7 as the header value, pole value in the queue. So that will be initialized to node. So now in this case, node is not equal to null, but you're getting flag equal to true. That means you have encountered null value somewhere between before only. So at that time, you will tell that the tree is not a complete binary tree. Uh, I don't know whether you have got it or not. I'll explain this properly when tracing the code. So yeah, if this is if all the cases are passed, that means you have not encountered any null values or you encounter null values and each time uh, the flag was true only, then yeah, you return just true. If you do not come to this case, once you encounter flag equal to true, then you return true. Now we'll run this. Why is it telling time limit exceeded? Any mistake in the code? This is fine. Add dot root, then node. Oh, it should be node value, node dot left, not root dot. So whatever element you remove, if you at first you'll encounter root as one, no? You have to go for one and you remove that from the queue and you won't find that in the queue. So you cannot do root dot left and root dot right because it will be empty by that time. That one will be initialized in node value. So you have to go from node dot left and node dot right. So now we'll trace this example. I'll just copy this code. Yeah. Okay, I just pasted the code and the diagram. Now we'll start with the first. So you'll initialize queue. Initially that will be empty, and then q dot root add of root. Root is nothing but one. So you add one to this. So once you add one, next bool flag will be set to false. So once this flag is set to false, you check whether queue is empty or not. Is it empty? No, it's not empty. So you go inside the while loop. So once you go inside the while loop, you create a new node where you initialize the value that is removed from the queue. So q dot poll will return. So if you do perform q dot poll, then one will be removed, and that will be added to the node value. Node will equal to one, and the queue since you have removed this one from the queue, now the queue will be empty. So queue is empty now, and node equal to one. So once you have node equal to one, now if node equal to null, you check no, it is not equal to null. Then else part you go. If flag equal to true, you check whether here is the flag equal to true. Is it true? No. So you check that part. Next you do q dot add of node dot left. What is node dot left? Add that to the queue. So q is equal to node dot left is nothing but 2 and q dot add of node dot right, that is nothing but 3. So why am I doing this? I am going in this order, first in, first out. So that next time when you perform q dot poll, 2 will be removed. So this is done. Next again you go the while loop. Whether queue is empty? No, this is not empty. Hence you go inside the while loop. Node three node equal to node dot q dot pole. So q dot pole 2 will be removed. So node will be equal to 2 now. And q, as you remove the 2 value, q will contain only one element, that is 3. So now whether you check whether node equal to null, no, it is not equal to null. Hence you go next part. If flag equal to true, no, it is not equal to true. It is equal to false only. Next q dot add of node dot left and node dot right. So now for that q you will add node dot left. So 2's left is 4. So 3 here, 4. And q dot of node dot right. Node is something with 2. 2's right is 5. So Q is containing these many elements now. Next again, when you check whether Q is empty or not. No, it is not empty. You go inside the loop. Next node equal to Q dot pole. So you remove 3 now. So now node will be 3 now. So once node equal to 3, when you check you if node equal to null or not. No, it is not equal to null. You go to else part. If flag equal to true, no, it is false only. Next, you just perform Q dot add of node dot left and node dot right. So 3 dot left. What do you have here? It is just null. So Q equal to, so once you remove 3, Q will contain what Q will be nothing but 5 comma 4, nothing else. So now you have 4 here, first 5, then node dot left, that is null, and node dot right, that is 7. These many elements Q is containing. So next you go again, check while condition. It is not empty, you go inside. Now node equal to Q dot pole, so node will be equal to, what is Q dot pole? You remove 9, right? So node equal to 9 and Q will be nothing but 7, null and 5. So node equal to 9, right? Or if node equal to null, no. Then if flag equal to true, it is false only. You just perform q dot add of node dot left and node dot right. So what is node dot left? 9. Sorry, is it 9? It's not 9, it's 4. Yeah, it's 4 actually. So this is 4. I misread this. So this is 4. So 4 dot left and 4 dot right. 4 dot left and 4 dot right. Both are null. So you just add uh, them to the Q. So Q will be equal to 5 null, then 7. 4 dot left is null, 4 dot right also null. So next again you perform while Q is not empty. Yeah, it is not empty. 3 node equal to node dot 4. So node will be 5 now. So once you remove 5, Q will contain null, null, 7, and then, so once you do this, you check whether node equal to null, node is not equal to null. You go here, whether flag equal to false, uh, flag equal to true. Is it true? No, it's not true. So you return, you will not check this condition, check that out. Next, you perform q dot add of node dot left and node dot right. What is node value? 5. So 5 dot left and 5 dot right both are null. So you just add them to the key. So n null 7 null null. All these are previous values. Now node dot left, node dot right both are null. So two more nulls. So you have this in the queue now. Now you whether you go inside the loop again, whether queue is empty, no, it is not empty. Then again you perform node equal to q dot pole. So node equal to q dot pole now it is containing null value. Hence node will be equal to null value. It's null. So once you have this as null, you check whether node equal to null. Yes, it is equal to null. Hence your flag will become true now. So flag equal to true. This is important. So once you have flag equal to, else part is not required. Next again you check whether okay. Once you remove this node, you will have only these many remaining elements now. So is q equal is not equal to null? Yes, it is not empty. Not equal to null. Sorry, it's is it empty or not? No, it's not empty. So you go inside the while loop, and next node equal to q dot pole. So what is q dot pole now? 7. So node will become 7 now. So once node is 7, now check if Node equal to null? No, it is not equal to null. So you go to the else part. If flag equal to true, yes, it is true. Previously it was true. Hence you return false. So you got this, I hope. What are we performing is we are inserting an element to the queue and we are popping that out. And while popping that out, we are checking if that value is null or not. If it is null, then you what set the flag value equal to true. If once you set the flag value equal to true, all the flag values next to that must be true only, because that you should get null values only. That means you should get every uh, node value as null. Once you get some node value as a null, only then it can be a complete binary tree. Because in this case, once you encounter null and you are encountering a not null value, so in that case it won't be a complete binary tree. If this was a null actually, then it would have been a complete binary tree. So once you get node equal to true, you set flag equal to true. So after setting flag equal to true, if in some case node is not equal to null, but you're getting flag equal to true. So once you set flag equal to true, you're getting this node value as 7, no? And you are having flag equal to true. That means at somewhere before you have encountered some null value and now you are encountering a node with some not null value. So that means that is not a complete binary tree. This is how we trace this question. I hope you guys have understood the problem. If you have any doubts, please drop it in the comment section. We'll come up in another video in the next session. And until then, subscribe to the channel and like and share it. Share it. Thank you.